How is everybody today? Happy Wednesday.
Pretty good. Just about to eat an entire pizza.
What kind of pizza you got?
It's like a frozen Tony's pizza.
Ah,
Super good.
Tony's is all right.
The rest of us?
What was that?
Do you bring some for the rest of us?
No, I'm eating the entire thing myself.
All right. As long as you share it with everybody in the room you're in.
Yeah, it's my bedroom stuff. Sure, it's myself.
Excellent. All right. Cool. So let me start off with an announcement. I posted this in Canvas already, but I want to also make an announcement of this in class right here. So a student in this class has a documented disability that impacts his or her or their ability to take comprehensive lecture notes. We are requesting that someone, preferably two of you, volunteer to share notes. And so I'm supposed to ask if there's anybody who would be willing to share their notes. And if yes, go ahead and send me an email and let me know, and I will send you a link for how you can register with the DSS office. And so you don't have to tell me now, but if you want to volunteer right now in chat, you can do that also. But send me an email, and I'll send you a link. All right. Any further questions from last time? We were finishing up some topics in number theory, some applications. We did some crypto, and we also talked about the midterm. And so, any questions on any of that?
I'm actually concerned. This is the third remove in a row from Callum. What if he's actually being hacked?
That would be bad.
I don't remember. What did we leave off with last class?
So last class we finished by working through the RSA public key encryption algorithm, and we just kind of did the very high level overview of the algorithm, and sort of waved our hands a lot to see kind of all the different parts and pieces.
We mentioned the homework for the programming assignment, right? Yeah, when's that due?
Check Canvas. I don't remember. I think it's next week sometime. But I do remember it's due at 8 a.m., not at 1, so.
Oh, okay.
I have a question.
Yeah.
When it comes to these mathematical equations that we're supposed to be implementing into a for loop, I'm having a really hard time deciphering or like breaking up the math problem so that it will work in a for loop. Is there any way that we can walk through that?
What kind of functions are you thinking about?
Well, for example, one our project that I don't know how to explain it. The summation symbol with the I underneath and the N, and then it'll have like the rest of the math on the right side. I'm having a really hard time like processing how that is supposed to be placed or implemented in code.
Okay.
Because I can see how it's supposed to be done in my head. Like, I understand how I could process a problem like that, or do algebra, or fix or do that kind of problem, like limits and calculus and that kind of thing. But to place it in code is kind of a different beast.
Okay, sure. So let's just do an example. Let's suppose that you're trying to calculate sum from I equals 1 to n of I squared plus 7. Random function, but something to work with. So so the summation says we want to iterate. We want to do something in a loop. This tells us that as we do this loop, we want to change the value of I, and we want it to run from 1 to n. So this I can sort of put directly into a for I equals 1, I less than or equal to n, I plus plus. And I need to calculate I squared plus 7, so I times I plus 7. And the summation symbol says each time I calculate this, I want to add it to a running value, a running sum. Running sum is just, a sum that starts at 0 and you keep adding to it. So it's an accumulator. And since we want to save the result in y in this case, I'll just start off with, integer y, and I'll initialize it to 0. And then in this loop, I'll say y equals y plus the thing that we're supposed to be summing. And when we come out of the loop, right, y should be all set. That should now be the sum expressed by that summation symbol. And whatever the expression is that goes in here, right, we just want to calculate that and add it to what we're using for our running sum, which, in this case I made it y, because that's what we were putting, on the left side of this. But if we didn't have something in particular we were assigning this to, I could just call this sum or something, initialize sum to 0, and say sum equals sum plus that expression, and it would do the same thing for us. It would calculate the result of doing this. Right, it's basically calculating that expression. Does that help?
Yeah, just a little bit.
Okay. And so for 222, this is, part of how we're calculating the hash function. And so same idea, initialize the sum to 0, and then do, I think it's I plus 1 times I plus 1 times plate bracket I. And in that case, I is going to go from 0 to string length of plate minus 1. So the conditions here get a little different, but basically lower limit, upper limit. I don't know if for loops were created with the idea of implementing summations. I kind of suspect they were. Because
I was talking with somebody who basically said that basically while loops aren't really necessarily used later on in a career-based, and it's for loops that are basically being used because of this kind of algorithm, because hashes are used more often in a business.
Interesting. So I would have thought the opposite, because
and this person's worked in a lot of different coding careers as well.
That's an interesting observation then.
Like while loops just aren't used. They're very simple when you're learning, but for loops are really the way that they structure stuff.
Huh. That's interesting.
For going over data and whatnot, it's nothing but for loops, but the only time that I'd say while loops would be used would be when getting user input. I mean, other than that.
Yeah.
That's interesting, because I rarely use for loops except, when I'm trying to iterate over a range of values. So if I'm trying to, turn on 10 switches, I'll do a for I equals 0 to 9 or 1 to 10 or something. But most of the time I'm doing while loops. And in fact, when I was teaching 120, I never talked about for loops because we used MATLAB, and MATLAB does weird things with for. But it's very natural to create a for loop using a while. It's a little weird to create a while loop using a for, even though you can do it. So that's an interesting observation. I wasn't aware of that. But I haven't coded for industry for a long time, so that's an interesting trend. And assembly language, it's all just go-tos, usually. All right, other questions or comments? All right, let's look at your next homework 6. And so I posted this morning on on Canvas. And it's a series of questions related to the number theory stuff we were doing last week. So the first one, calculate 2 raised to the 130th power modulo 7. In other words, when you take 2, multiply it by itself 130 times, and divide by 7, what is your remainder? It'll be 0, 1, 2, 3, 4, 5, or 6. And I want you to do this. Go ahead.
That 2 star star is raised to?
That's exponentiation. Yeah, that's raised to.
Okay. I'm used to like the little upward arrow. But
Okay. Let me clarify that in here. Because that's not standard notation. That's actually a programming syntax more than anything.
Thank you.
Yeah, thank you. So yeah, 2 raised to the 130th mod 7, and I'd like you to do this calculation using what we called modular exponentiation, which was the idea of first calculating 2 to the 1st, 2 squared, 2 to the 4th, 2 to the 8th, 2 to the 16th, 32nd, 64th, and 128th. And so you do 8 calculations, each of these based on the prior calculation by just squaring the result of the prior. And then once you've got all of these calculated, if you take 2 to the 128th times 2 to the 2nd, that should give you 2 to the 130th. And each of these will be a number between 0 and 6, and so multiplying these is not, involving very large numbers. But that's the technique we went over in class, and that's the technique I want you to do. Now, if you Google what is modular exponentiation, it'll say, do 2 to the 13th and then multiply by 10. That's 2 to the 130th, right? That works, but that's not the algorithm. And we want an algorithm so that, if we wanted to, we could teach a computer how to do this. So modular exponentiation is this very specific set of steps you follow. So I'm looking for you to recreate those. And then 2 to the 6002 mod 7 using Fermat's little theorem. And the hint here is, Fermat's little theorem mod 7 tells us 2 to the 6th is congruent to 1 mod 7. That's a direct application of Fermat's little theorem. And if we know 2 to the 6th is congruent to 1, you can use that to calculate 2 to the 600th or the 6000th modulo 7. And if you know what 2 to the 6000 is, calculating 2 to the 6001, just multiply by 2, 2 to the 6002, multiply by 2 again, and you're done. So think about that, go back to the example we worked through in class, and this is a pretty quick calculation to make. Please don't multiply 2 by itself 6002 times, unless you really, really want to. All right, question 3, we're looking at modulo equivalences. And remember, 2 numbers are equivalent mod n if their difference is divisible by n. So this is using this definition. A is congruent to B modulo n if and only if n divides A minus B. But equivalently, this means that when you divide A and B by n, you get the same remainder. Whereby the remainder, we mean the remainder between 0 and n minus 1. So for example, 26 and 2, their difference is 24, that's divisible by 8. So these are congruent to each other. The equivalent statement is if I take 2 and divide it by 8, I get 0 with 2 left over. If I take 26 and divide it by 8, I get 3, again with 2 left over, 2 more than 24. The fact that they both have the same remainder when you divide by 8, that also tells you that they're congruent to each other. But you can always use the most formal definition, which is n divides their difference. And so it's kind of a direct application of that to answer these 6 questions. But you can also think about them, and there's other ways to interpret these questions, such as, remainder when you divide. All right, question 4, we're just looking at prime numbers and non-prime numbers, which are called composite numbers. And so for each of these, tell me if it's prime or composite. And if it's composite, it means it has a factor other than itself in 1. Tell me what one of those factors is. And you can put these into Google and say is 91 prime and so on, but you know, do this by hand. Have some experience with these numbers, just to kind of get a feeling for them. Question 5 is similar. Take each of these numbers. These numbers are not prime. Write them as a product of prime numbers, or powers of primes. If you don't want to write, you know, 2 times 2 times 2 times 2 a bunch of times, you can put powers. But we have this thing called the fundamental theorem of arithmetic, which says any number can be written uniquely as a product of primes. And so let's just go ahead and take these numbers and write them out as products of primes. And then 6 is playing around with greatest common divisors. So Euclid's algorithm, that procedure that we talked about to find the greatest common divisor of two numbers, you write this is something times that plus a remainder. Then you take these two and you bring them over to the left on the next line. And this is something times that plus a remainder. And you keep going till your remainder is 0. So use that algorithm to find the GCD of these 5 pairs of numbers, 115, 1066, and 572, etc. So this is a very different kind of exercise from the proof homeworks, right? Where you've got to figure out the right way to look at this and then you know, list the steps and so on. These are much more procedural. In fact, all of these questions, we could write a computer program to do these, right? And say, you know, here's a pair of numbers, tell me what the GCD is. Here's a number, tell me what the factors are for it. That's all stuff we can teach a computer to do. So this set of questions is more procedural than the others. So it's kind of a nice, you know, counterpose to doing proofs for this week. All right, and so those are due a week from today. Any questions about any of that?
Gonna have to be going back and rewatching the videos.
Yeah, that's cool.
Yeah,
Or-
I want to rewatch the lectures.
Or check your notes too. And if you're not making notes during class, at the very least, I recommend go back and watch the videos and make notes from those. And keep a set of notes that you're building throughout the course. And then, you know, when you get to an exam, when you get to a homework question, you've got notes you can refer to. And if you don't have the right things on your notes to do the homework, right, that's your chance to add things to it. If you notice that there's things on your notes you never use because you've already memorized them, right, well, you can take those off your notes. And then, you know, rewrite your notes periodically, maybe at the end of a unit and so on. And then when we get to the exams, right, you've got your note sheets already. And they're field tested and ready to go. That can be one way to sort of try to digest the information that's coming out in the course.
I've never thought about rewriting notes. Is that like a common thing?
I think it is, yeah. Because they're kind of an organic document. And so if you don't have, you know, recorded lectures, mostly when I was in school, people would just furiously, you know, scribble down whatever the teacher was saying. Teacher sneezes and you write down sneeze, you know. And then you've got a jumble of stuff, you know, and you try to pull the meaningful stuff out of it. But you know, since the lectures are recorded and tagged and stuff, you know, hopefully a lot of the time spent in class is spent listening and thinking about the material, but also maybe, you know, jotting down some major themes or things that strike you as this is particularly interesting or important or something. But yeah, as you use your notes for homework and for studying and so on, you'll usually find things that are omitted from there or things that don't need to be on there anymore. And so, you know, you can like lightly cross things out or write things in, but eventually your notes become this kind of jumble of, you know, what is this? And then that's a good point to rewrite it. And rewriting it is actually a useful way sometimes to help, you know, learn the concepts more clearly, because transcribing something, the act of, you know, physically moving a pen and seeing what you're writing and that kind of stuff, It's a different way that we code information. And that can be helpful for not only, you know, remembering it, but also for kind of conceptualizing it in a different way. And so yeah, when I study stuff on my own, I fill notebooks full of notes, and I periodically, you know, rephrase what I've learned so far and so on. This is all great.
Take a single note
Say what?
in any of my CS courses.
Oh yeah? Cool.
How do you
A
survive?
lot. I don't
The
know.
only notes I used on the exam were the list of different logical statements
same.
and stuff like that. Yeah.
Oh, okay.
Disjunctive simplification, just because I forget the names and what exactly they are.
Okay. If that works for you, that's great. I wrote so many notes when I was in school.
Because you have the lectures recorded, and so I can pay attention in class, like pay attention to what you're saying instead of missing something you might say if I'm writing something down.
Right.
I believe that's something I can go back into your video catalog for clarification. So I like the way you have it set up.
Okay, cool. That makes sense. Yeah, I took so many notes when I was in school, and a lot of them I never looked at. Some of them I did. But largely when I study stuff on my own, I mean it's all note taking. It's trying to understand stuff that I'm reading, and I kind of get it, but maybe not quite. And so, you know, I'll write it down, and it might not even make perfect sense to me. But I can go back and look at my notes instead of going back and looking at, you know, these 10 pages from a textbook. So it's a process sometimes of trying to get to that nugget of information that's buried inside the presentation, and that for most of us, I think it takes, you know, multiple iterations of going through it. I haven't done College 101 here. I'm curious if they talk about things like, you know, note taking skills and
No.
stuff like that. I should talk more about that in CSE 101 probably. Because those are things that don't necessarily come up in high school, and it's part of that transition to college where it's like, you know, at some level it's your choice what you get out of the material, and if you don't know that and you don't know ways to increase that experience, it's, you know, kind of a shock for a lot of students. It shocked me when I started college. It's interesting. All right. Any other questions up to here? All right, so let's talk about a journey of 1,000 miles. Right? Your goal is to walk 1,000 miles. And I don't know where that takes you from here. Somewhere in the mountains, I guess, unless you go south. But let's, you know, there's this expression, this saying that a journey of 1,000 miles begins with a single step, right? And that's certainly true. If you don't take a first step, you're not going to be able to walk 1,000 miles, right? That's pretty clear. If you do take a first step, does that really help you walk 1,000 miles? We could write an algorithm for how to walk 1,000 miles. And we could write it as, you know, put your left foot down, put your right foot down, repeat this, you know, I don't know how many million times. We could put it in a for loop or something, right? Assuming we knew how many steps it would take and so on. But there's a different way we could think about walking from point A to point B, right? So an algorithm to walk from point A to point B, so I would say, you know, start at A and make sure you're facing B. So this is my algorithm for let's not get too jiggy with this. Let's just say let's walk to point B. So this is Seattle or something. We want to walk to Seattle. So walk to Seattle. All right. I can describe this as a two-step algorithm, assuming that you're outdoors and you're facing Seattle and you're standing up and so on. The first thing is take one step towards Seattle. And then the only thing you've got to do after that is walk to Seattle. And there's a two-step algorithm for how to walk from here to, you know, wherever. So take one step in the direction, and then do whatever you have to do to walk to your destination. Was there a comment?
I don't know where we're going with this, but couldn't you just make it a one-step algorithm?
What would that be?
Walk to Seattle.
Well, but I'd never end up taking a step, right? Because there's nothing in this algorithm that tells me to take a step. If my whole algorithm just says walk to Seattle, I'll just sit here and say, hey, I'm walking to Seattle. But this is what actually gets me closer to my destination. But there's nothing in here about take a million steps. There's nothing in here about take a step and then take another step and then take another step. But this will get me to my destination.
It's kind of like the how-to essays.
Yeah, yeah. All right. I need to modify my algorithm a little bit though, because if I'm in Seattle and I try to take one step towards Seattle, I'll either blow up because I don't understand the instruction, or I'll walk past Seattle if I'm walking north or something like this. So I'm going to add an extra step here. If already there, if already at Seattle, I'm not going to do anything. I'm done. Otherwise, I'll take one step towards my destination, and then I'll run this algorithm that I have called Walk to Seattle. All right, so let's keep that in the back of our brains, and we're starting off with some kind of hand-wavy, high-level examples, and we'll add more meat to this as we go. Let's look at climbing a ladder. So here's a ladder, and it has rungs on it. So each of these things that you can step on is called a rung. And maybe this ladder goes from here to the moon. So there's the moon, and it's got some craters on it and so on. And here's the Earth, right? And it's a really big ladder. And oh, how am I going to climb this thing all the way up to the moon? It's a really simple algorithm. 1, go up 1 rung. 2, climb to the moon. So my climb to the moon algorithm consists of 2 steps. First, go up 1 rung, so hold on with your hands and lift one leg and put it on the next rung up the ladder, and then use that to pull your body up. And then do whatever you have to do to climb to the moon.
I guess I'm still, I feel like, did I miss something?
Like what?
What are these algorithms supposed to be for, or?
We're describing a kind of far-fetched way to tell somebody how to climb a ladder from the Earth to the moon.
It's just a more abstract application of recursive function.
Yeah, yeah.
If that helps.
So it's a lighthearted exploration of an algorithm that involves calling itself. And if you know how to go up 1 rung on a ladder, that's all you need to know to climb that ladder as far as you would like. You basically just go up one rung at a time. And I
0
don't...
is if you're at the moon stay?
Yeah. And I don't need to describe in my algorithm, if I'm at rung 237, I should put my foot on rung 238, and then, you know, adjust this variable to 238 and repeat, right? It's the same 2 steps. Climb up one rung, and then run your, you know, climb to the moon algorithm, which tells you how to climb from where you are to the moon. And there's one thing missing in this that we've kind of assumed, but how do you begin this process? We need an extra step up here, which is, you know, stand on the first rung. If I'm not standing on the first rung of the ladder, I can't use this algorithm. If I'm, you know, over here drinking coffee, I can't go up one rung. Or, if this ladder did not touch the Earth, if this ladder started, you know, at the midway point between Earth and the moon, I could not use this algorithm because I have no way to get to that first rung. And if I'm not on a rung, I can't climb up to the next one. And so we need some kind of initial step and then some kind of repeated step.
Finding ladder or something.
Mm-hmm.
Build a really huge ladder.
Yes.
And hope you don't suddenly start speaking new languages. No, just kidding.
Yeah, we're not worried about oxygen and things like that, right? But, you know, why does this algorithm not work? Because at some point, this going up one rung is not going to be feasible. Because if I try to go up one more rung, I'm going to run out of oxygen maybe, you know. Or the ladder's going to break because it can't support my weight, you know, when I'm a million rungs up in the air. Or something like that, right? But theoretically, you know, if I can move from any rung to the next rung, I can get to the billionth rung, which is, you know, where the moon is. All right, so that's just kind of some initial kind of brain candy around the idea, but we can make this a lot more formal. And I'm going to have to block out the sun. All right, so more formally, this is going to lead us to a method of mathematical proof, and it's a method called mathematical induction. And so mathematical induction, our goal is that we're going to have a family of propositions. So given a family of propositions, say P of n, where n is an integer and n is bigger than or equal to 1. So we're working with a group of propositions, P1, P2, P3, P15, P10 million, P65 trillion, right? Family of propositions, theoretically an infinite family. So given a family of propositions, we want to prove P of n is true for all n bigger than or equal to 1, for example. It could be bigger than or equal to 0 or 5 or something, but we'll typically work with, you know, a family of propositions where n is bigger than or equal to 1, and our goal is to prove that all of these propositions are true. All right, so for example, let P of n be the proposition 1 plus 2 plus 3 plus dot 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 plus n. In other words, the sum of the first n integers is equal to n times n minus 1 over 2. So that's a family of propositions. N times n plus 1. So for example, P of 3 is the proposition that 1 plus 2 plus 3 is equal to 3 times 4 divided by 2. And that turns out to be true. So P of 3 is the proposition 1 plus 2 plus 3 equals 3 times 3 plus 1 divided by 2. Well, 1 plus 2 plus 3 is 6. 3 times 3 plus 1 over 2, that's 3 times 4 over 2, that's 12 over 2, that's 6. This is true. P of 5 is the proposition 1 plus 2 plus 3 plus 4 plus 5 equals 5 times 5 plus 1 divided by 2. Well, 1, 2, 3, 4, 5 added together is 15. 5 times 6 is 30 divided by 2 is 15. This is also true. If we knew that P of n was true for every integer n, we would have a handy little fact. We would have this handy fact that the sum of the first n integers is always just n times n plus 1 over 2. If someone said add up the numbers from 1 to 100, we'd say it's 100 times 101 divided by 2, that's 5,050. It's a really useful little fact. But before we can use this formula, we have to somehow prove that this is true for all n. Now, we've seen a couple of cases where it's true, and if you've studied this in algebra class, you may have seen a proof that this is true. But how can we show that this proposition is true? And we can't just try every possible value of n because there's an infinite number of values of n. So mathematical induction will be useful when we want to prove that a whole family of propositions is true. And so this is an example of a family of propositions that turns out to be true for all n bigger than or equal to 1. So here's how we can do this with mathematical induction. So we're given a family of propositions. If we can prove that P of 1 is true, and we can prove that if P of n is true, P of n plus 1 is true. Then we know P of n is true for all n bigger than or equal to 1. All right, this is mathematical induction. So mathematical induction says if we can prove a family of propositions that one of those propositions is true, say the proposition when n equals 1, and we can prove that if a proposition is true for n, it's also true for n plus 1, that's enough to prove that this proposition is true for all values of n. This has actually got to be for n bigger than or equal to 1. And so we can write this in our vertical theorem format. P of 1, P of n implies P of n plus 1, where n is any number bigger than or equal to 1, we can conclude P of n for all n bigger than or equal to 1. So that's the succinct statement of mathematical induction. All right, questions so far? So notice why we care about this, right? To prove P of n for all n bigger than or equal to 1, you got to do a lot of work. You got to prove P1, P2, P3, P4, P5, P6, P7, take a breath, P8, P9, P10, keep going. You never get to stop. You might prove P all the way up to 10 billion, and someone will say, what about 10 billion and 1? So you get a new piece of paper, you prove P 10 billion and 1, 10 billion and 2, 10 billion and 3, you get up to a trillion, and they say, what about a trillion and 1? You got to start doing more proofs. And you're never going to finish, because, you know, if n's an integer bigger than or equal to 1, there's no largest value of n. So proving each of these is impossible. We cannot do that unless we wrote an infinite number of proofs. Mathematical induction says we can prove this without proving, you know, an infinite number of statements. We only have to prove two things. Prove that P of 1 is true, and then prove that if P of n is true, P of n plus 1 is true. So if we do those two things, we end up proving an infinite number of things. And when you get like an infinite number of things for the cost of 2, that's worth taking a closer look at. So proving P of 1, this is called the inductive step. Sorry, this is called the base case. And this second thing that we prove, this is called the inductive step. If you're thinking a bit about CSE215, this is our recursive statement. This is that special statement we put in the beginning of our recursive functions that get us out of infinite recursion and avoid seg faults. We'll say more about that later. Alright, so we're going to prove two things, and then when we wave the magic wand that says mathematical induction, bingo, we've proven an infinite number of things.
Is P of 1? I just realized.
Is what?
So P is just the sum of all digits up to n, right?
P is a proposition, and I want to be really, really picky about terminology here, right? P is not a sum of integers. P is a proposition, and I think that's what you meant, but I'm going to be really, really precise in terminology, because this will steer you wrong when you try to do these. So P of n is always a proposition. But if we look at P of 1 is the proposition, which says 1 is equal to 1 times 1 plus 1 over 2. The sum of the first 1 integers, 1, should be equal to 1 times 2 over 2, and that is in fact true. It's kind of a...
I thought it was n plus 1.
Okay.
My bad.
Yeah, well, this is n... Oh yeah, n plus, right. Yeah, so it's times. And the base case often feels kind of reductive. The sum of the first 1 integers, well, that's kind of a weird thing to say in English, but, you know, it's just that 1 integer. All right, so let's do an example. Let's try to prove this formula about the sum of the first n integers. Alright, so we've got a proposition. P of n is the proposition that the sum of the first n integers is n times n plus 1 over 2. So, let me rewrite this. And we've got to be a little careful with dot dot dots. Really what we're doing with mathematical induction is eliminating the need for dot dot dot. And so I could write this as a summation symbol, but we're going to get all tangled up in details of summation symbols. So I'm going to be a little carefree and use dot 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 here, but we're not going to get too overboard with it. We're not going to use it to cheat. So this just means, you know, the sum of the first n integers, and we claim that that's equal to n times n plus 1 over 2. That's what p of n says. P of, you know, 50 could be true, could be false. Don't know yet. So our goal is to prove p of n for all n bigger than or equal to 1. And I'm not going to keep saying n is an integer. We're going to assume that, you know, we're working over integers. And so I want to prove p of n. And terminology here, or symbology, if I just say prove p of n, it means prove p of n is true. Sometimes we might prove something is false, but in general, if we just say prove this proposition, we mean prove that it's true. So let's prove p of n is true for all n. So step 1, this is the base case. So here's our proof. Step 1 base case, we need to prove p of 1. Alright, how do we convince the reader that p of 1 is true? Let's write out what p of 1 says. P of 1 says 1 is equal to 1 times 1 plus 1 divided by 2. And I'm just going to say this is true. I could, you know, write this as 1 times 2 over 2, 2 over 2, 1, but I'm going to assume somebody reading this is able to pretty easily see that this is a 1 and calculate this and see that it's a 1. And usually proving the base case is no more complex than that. It's usually pretty trivial to see that this is true, but it's an important step. Alright, now, according to mathematical induction, I need to do one more thing. I need to prove what we call the inductive step. I need to prove that Pn implies P of n plus 1. So this is going to look like a proof from a few weeks ago. So 2, prove P of n implies P of n plus 1, where n is some number bigger than or equal to 1. And I'm going to do this very much like the proofs that we've been doing. So step 1, I'm going to state the hypothesis. I'm going to say P of n is true. The reason, that's a hypothesis. This is like saying, you know, n is even, or you know, A divides B. It's the if part of our if-then that we're trying to prove. And just like, you know, when we say n is even, A divides B, that kind of thing, my next step is to write out what this actually means. And, you know, I've written at the top what P of n says. Well, if I'm saying P of n is true, I am also saying 1 plus 2 plus dot 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 plus n is equal to n times n plus 1 over 2. Why is that true? That's the definition of P of n.
Couldn't you do this with like the summation formula or something to be?
Yeah, I could do a summation formula over here and it would be a little cleaner. But it's another layer of mathematical symbology we can get lost in. And my goal is to focus on a different part of this process. So for now, I'm going to be kind of informal and do this dot dot dot. All right, now I'm going to do something that may feel totally unmotivated. What I'm going to do is add n plus 1 to both sides of proposition 2. This is still a proposition. It's a declarative statement which claims that this sum is equal to this expression. And it has a truth value. It's true or false. I don't know which it is. But it's a proposition. I'm going to create a new proposition which, if this is true, this new proposition will be true. And this new proposition is going to be the statement that if I take this and I add something to it, I get the same thing as if I take this and add the same something to it. right? If this equals that, this plus 5 equals that plus 5. This plus 10 equals that plus 10. So given that this is a true equality, I can add whatever I want to both sides, and this will still be an equality. That's just a algebra thing, right? So I'm going to add n plus 1 to both sides of an equality, and this will still be a true proposition. 1 plus 2 plus dot 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 plus n plus 1 equals n times n plus 1 over 2 plus n plus 1. And that's undeniable. Now this may or may not be true. Right? P of n could be the proposition that 1 equals 2, or n plus 1 equals n plus 2. But we're assuming P of n is true, and that means this is true, and that means this is also true.
I have a question.
Okay.
Wouldn't just adding one number to both sides make it somewhat redundant?
Normally, yes. But in this case, it's going to get us something really interesting. It's actually going to get us P of n plus 1.
Okay, then I'll just follow the process and wait till
Okay.
because right now I'm just kind of like that. Why? This seems like an unnecessary step.
And this is totally uninspired at this point, right? We have no particular reason why we're adding n plus 1 to both sides. But we'll see what it does, and then we'll go back and we'll figure out, well, how did I know to add n plus 1 to both sides? And what should I add for a different problem, and so on. But for now, let's just settle with the fact that this is a true proposition, because this is a true proposition, and I just added n plus 1 to both sides. But now I'm going to do some algebra, and I'm going to say 1 plus 2 plus dot 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 plus n plus 1 equals, and I'm going to start doing a bunch of algebraic manipulation. So I'm going to do n times n plus 1 over 2. I'm going to write that as n squared plus n over 2, and I'm adding n plus 1. And now I'm going to put this over a common denominator with that and write this as n squared plus n over 2 plus 2 times n plus 1 over 2 plus, which is equal to n squared plus n over 2 plus 2n plus 2 over 2. And I'm going to go on, which is equal to, and now I'm going to combine these, n squared plus n plus 2n plus 2 over 2, and I'm going to factor and write this as n plus 1 times n plus 2 over 2, because this is n squared plus n plus 2n is n plus 2n plus 2. And so what I've done is I have done with algebra a demonstration that this is equal to that. And my reason is, lots of algebra. Well, I've just stated a new proposition, and I've demonstrated this new proposition is true. And this new proposition is that the sum of the integers from 1 through n plus 1 is n plus 1 times n plus 2 over 2. Well, if I look at my definition of P of n says the sum of the integers 1 to n is n times n plus 1 over 2. If I tried to write P of k, that would be the sum of 1 plus 2 plus dot 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 k equals k times k plus 1 over 2. But for this proposition, what does P of n plus 1 say? It says if I do 1 plus 2 plus dot 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 plus n plus 1, I should get n plus 1 times n plus 1 plus 1 divided by 2. In other words, proposition n plus 1 says the sum of the first n plus 1 integers is n plus 1 times n plus 2 over 2. Well, guess what? That's what we just demonstrated. Right?
Well, can you go back a little bit? Because I'm still trying to figure out how those equate to each other.
These?
Yeah.
So I'm using this definition of P of n, which says add up the first n integers, it's n times n plus 1 over 2. So n plus P of n plus 1 says if I add up the first n plus 1 integers, I get n plus 1 times n plus 2 divided by 2.
Maybe I'm just rusty.
That makes sense.
Let me try it like this, because this is a fairly bizarre point. So let's do it like this. P of k is the proposition 1 plus 2 plus dot 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 plus k equals k times k plus 1 over 2. Okay. If k happens to be equal to n plus 1, right, well, this is P of n plus 1 is the proposition that 1 plus 2 plus dot 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 plus, in this case, n plus 1 equals k, n plus 1, times k plus 1, which will be n plus 2, divided by 2. And this is really just a placeholder. This could be a number, it could be an expression, it could be another variable. So in this case, in place of this placeholder, I'm putting n plus 1. In place of this, I'm putting n plus 1. Here's n plus 1, here's n plus 1.
Oh, I see the correlation now.
Okay, cool. Alright, so that's key, right? Because with that observation, P of n plus 1 says this is equal to that. Well, guess what? In step 4, we just showed that this sum is equal to that. We just proved P of n plus 1. And so step 5, we simply state P of n plus 1. And that's the definition of this family of propositions combined with the proposition we stated in 4. Well, now we're all set, right? We started with P of n, we proved P of n plus 1. So now we can say, therefore, P of n implies P of n plus 1, and that's what we were asked to show for this part of the proof. Okay, now we've got two things we've proven. We've proven P of 1 is true, and we've proven P of n implies P of n. So now we can say, therefore, P of n is true for all n bigger than or equal to 1, and the reason for that is mathematical induction. And here's our big QED, because that's what we were trying to show, trying to prove P of n for all n.
I see now why we left the dot dot dot.
Yeah, it just makes it a little easier.
That's a pretty interesting way to go around solving it. Could you do something similar by multiplying by n plus 1?
If we were trying to prove a proposition, a family of propositions that involved multiplication, we would probably end up doing some kind of multiplication in our proof of the inductive step. But this is always kind of the big sort of pinch point in these proofs. Like, how do you know to add n plus 1 to both sides? And we'll talk about that, but it's similar to the question of when you're trying to prove A divides B plus C, how do you know to substitute K times B in place of A, or something like that? There's always some point in these proofs where it's like up to here is pretty straightforward. From here on is just a lot of algebra, but there's some bridge step in the middle. And we'll do a lot of these proofs, and we'll see a lot of these bridge steps, and we'll talk about ways to help us see, you know, how to bridge from the earlier steps to the later. So this is a powerful result, right? We've proven that this formula for adding up the first n integers always works, always. For 1, for 2, for 3, for 100, for 1,000,000, for 1,000,000,000. And to do that, all we had to do was show that it works for one case, and then we had to show that if it works for n, it works for n plus 1.
I take it there's also a way to do this the backwards way?
You can, but we usually do it in this direction, starting with 1 and building up. There are things like methods of infinite descent, where sometimes we start with a number and we prove it for smaller and smaller values. But typically we're trying to prove it for values going up to infinity, right? Numbers that get bigger and bigger. All right, so a really good question at this point is, why does this work? And it's really just the chain rule. So suppose I want to prove, let's use the same proposition, and I want to prove P of 5. And somebody says, oh, you know, I know it's true because of this mathematical induction thing. And you've never heard of mathematical induction, right? You don't know anything about this. But the person tells you, hey, here's two things I've proven. I've proven P of 1, and I've proven P of n implies P of n plus 1, where n is bigger than or equal to 1. And you've never heard of mathematical induction, but you've been told these two things are true. Here's what you can do. And this is the whole heart of mathematical induction. I can say, hey, P of 1 is true. I know that because the person told me it's true. If I look at this statement and I think of n equals 1, what does this tell me? This tells me that P of 1 implies P of 2. P of n always implies P of n plus 1. So P of 1 implies P of 1 plus 1, that's P of 2. And I also know from this statement, if I think of n as being 2, that if P of 2 is true, P of 2 plus 1, or 3, is true. And the same statement tells me, hey, if P of 3 happens to be true, don't know if it is, but if it happens to be true, P of 4 will be true. And by the way, this statement also tells me if P of 4 is true, P of 5 is true. And now, sorry?
All the way to infinity.
Well, I'm going to stop at 5 because my only goal today is to prove P of 5. That's what this person challenged me to do. So I'm going to stop here, but I could go on, right? But I'm going to stop here, and I'm going to use the chain rule. I'm going to say P of 1 implies 2, 2 implies 3, so 1 implies 3, and 3 implies 4, so 1 implies 4, and 4 implies 5, and I'll do a bunch of chain rules, and eventually I can show P of 1 implies P of 5. And now, you know, I've got P of 1, I've got P of 1 implies P of 5. I can put those together with detachment, and that will tell me P of 5 is true, and I'm done. But that's a lot of work, right? But you know that you could do that. If someone said, I'll give you $1 million if you prove P of 100, you could do it. You'd have to write down, you know, 100 statements, and you'd have to list, you know, chain rule next to a bunch of them and all this kind of stuff. But no doubt you could absolutely do that. For $1 million, you'd do it on a nice clean sheet of paper, and you'd write really neatly and so on. And in the end, you'd say P of 100 is true. So mathematical induction tells us that we're safe in assuming that we can always do this. As long as we know these two things, it's saving us from having to go through all of these steps. It's saying, hey, you can just leapfrog from this and this. You can conclude P of n for any n bigger than or equal to 1. And if it's true for any n, it's true for all n. That's all that's really going on. So given these two things, you don't need to know mathematical induction. You can leapfrog your way up to eventually proving P of n for, 5 or 10 or 100. But if you wanted to prove P of 1,000,000, this is a really long proof. So we prove these two things and we say, therefore, by mathematical induction, P of 1,000,000. But we know more than just P of 1,000,000. We know P of every integer is true. So we get all those results for free. All right. Let's do a 5-minute break and let that bake in our brains. And let's come back at 2:11, and then we'll start going through some more examples of this, and we'll go through some mathematical examples, and we'll go through some non-mathematical examples. And as we do this, we're going to keep thinking about this idea that we're proving something about an infinite family of propositions by just proving two very specific propositions. All right, so I'll see you back in about 4.5 minutes, and we'll continue with that.
Between now and then too. We're getting an Amazon Fresh. We're getting a grocery delivery between 3 and 5. So if you see that happening, that's easier. Yep. Oh, we've done it. It feels great. Yeah, it's contactless. They just drop them at your front door.
Hey, how's it going?
They're going overseas in the car.
Excellent.
Yeah.
Are you going too?
No, I'm picking Greg.
No, I meant Burns.
Oh.
Yeah, you gonna skate?
Yeah.
No, okay. We can set you up.
Okay.
put some butter on the bottom of your shoes.
Have fun, you guys.
Okay.
Have fun.
Call me if you get lost. He said he might have to come back and use the bathroom.
That's
So I'm gonna leave the front door unlocked for them.
Yeah, we won't charge them.
Yeah.
Whoa. Oh, no, it's be a squirrel hero. Alrighty. All right, so let's see some more examples of mathematical induction. So let's try another mathy type example. Let P of n be the proposition 1 plus 3 plus dot dot dot. Let's do, let's go up to n. And so the sum of the first, the odd numbers from 1 through, let me do this differently. So the first n odd numbers, and this will turn out to be 2n plus 1, but I don't want to get bogged down on that detail of it. So P of n is the proposition that the sum of the first n odd numbers is equal to n squared. So for example, the first 3 odd numbers, 1, 3, and 5, if you add those together, you get 9, that's 3 squared. 1 plus 3 plus 5 plus 7 is 1 and 3 is 4, 5 is 9, 7 is 16, and that's 4 squared. So the sum of the first 4 odd numbers is 4 squared. Alright, so that's what our proposition is. But let's write this more mathematically. So the first n odd numbers, this looks like 1 plus 3 plus dot 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 plus. So the first odd number is 1, second is 3, third is 5. So the nth odd number would be 2 times n minus 1. Alright, so for example, P of 2 is the proposition 1 plus 3, because 2 times 2 minus 1 is 3, is equal to 2 squared. And that's true. P of 5 is the proposition that if you add the odd numbers from 1 up to 2 times 5 is 10 minus 1 is 9, so 1 plus 3 plus 5 plus 7 plus 9 is supposed to be equal to 5 squared. Well, 9 and 7 is 16, 21, 24, 25, 25. This is also true. Alright, so let's prove this using mathematical induction. So let P of n be the proposition 1 plus 3 plus dot 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 plus 2n minus 1 equals n squared, where n is an integer bigger than or equal to 1. And we want to prove P of n is true for all n bigger than or equal to 1. So remember, this part of it is just stating a proposition. We're not saying it's true or it's not true. That's simply the definition of P of n. And for any integer n, P of n is a new proposition. But our goal in this problem is to prove that P of n is true for all n. So P of 1, P of 2, P of 3, P of 5 million. We want to prove that all of those are true. Walnuts? Excellent.
Double bust.
And we're going to prove this using mathematical induction. So to do that, we have to use 2 steps. Step 1, this is the base case. And we have to prove P of 1. Well, how do we do that? Let's just state what P of 1 says. P of 1 says that if we add the odd numbers from 1 up to and including 2 times 1 minus 1, that's 1. So it says 1 equals 1 squared. And we can see pretty clearly that's true. So P of 1, not a problem. Step 2 is the inductive step. Prove P of n gives us P of n plus 1. Where n is some integer bigger than or equal to 1. And again, it's important to note, we're not proving P of n, we're not proving P of n plus 1. We're proving this conditional statement. If this is true, then that is true. And that's usually a lot easier than just proving this for all n. This is a single proposition. Right? It's a proposition that if P of n is true, P of n plus 1 is true. Alright, so let's do this inductive steps proof. And let me do this on a separate page. And we'll proceed like our usual proof. Step 1, I'll state that P of n is true. This is the hypothesis. Step 2, I'm going to write out what that means. I'm going to use the definition of P of n to rewrite this as a more useful proposition. 1 plus 3 plus dot 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 plus 2n minus 1 equals n squared. That's what P of n tells us. So at this point, I'm going to make one of my ignore sections. This is where I'm going to think out loud on paper. And I'm going to say I want to prove P of n plus 1. Right, that's my goal. I'm assuming P of n. I want to eventually get down to a proposition which is P of n plus 1. Well, if I'm going to try to prove something, it's nice to be able to see what it is that I'm trying to prove. So I'm going to write out P of n plus 1. P of n plus 1 says, well, it says if I add up the first n plus 1 odd numbers, so 1 plus 3 plus dot 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 plus 2n minus 1, that's the first n odd numbers, plus the next odd number after that, which is 2n plus 1. That should end up being equal to n plus 1 squared. So that's what I'm after. If I can prove this is true, I've proven P of n plus 1. I've proven that this implies that. I'm done with my inductive step. I can say mathematical induction, and I've proven my original goal, P of n is true for all n. So now I've reduced my entire problem to this one kind of sub-problem, which is proving that this is a true proposition. And so you have that, safely on your ignore section, and you look at what you've got so far. Well, I've got, all of this equals n squared. I'm trying to show all of this plus 2n plus 1 equals n plus 1 squared. And it's not clear how to turn an n squared into an n plus 1 squared, but it should be pretty clear how to turn this into this. Because all I got to do is add 2n plus 1 to this, and I've got that. And so that's my idea. Add 2n plus 1 to each side of the equality that we have for p of n. Add 2n plus 1 to both sides of this. Okay, that's the magic step in this case that's going to take us to the conclusion. Why is it 2n plus 1?
Yeah.
Because I observed on here that the thing I'm trying to prove, right, compared to what I know so far, well, you know, I've got some sum equals n squared. I'm trying to prove some other sum equals n plus 1 squared. And it's just the observation that this left hand over here is really close to this left hand over here. And that if I were to add 2n plus 1 to this, I'm going to get this. And that's half of what I'm trying to show. That's one side of what I'm trying to show. And maybe this will not lead to anything. But it's a flash of inspiration that, like, hey, maybe if I add 2n plus 1 over here and here, maybe I can turn that into this proposition. And that's my sub-goal right now. So we're going to try it. And, you know, sometimes you'll get these ideas and you'll try it, and they won't lead you anywhere. And so your intuition led you astray. And the next time your intuition will, you know, have a more refined algorithm, and you may find a different approach. But for most of what we're going to do here, this first intuition will usually take us in a good direction. So let's just do this. Let's add the same thing, 2n plus 1, and this is just, you know, add 2n plus 1 to both sides of the proposition we wrote in step 2. And we're going to see if this gets us anything. Let me make this a little neater because this is key. Well, I'm going to rewrite the left side as is. And n squared plus 2n plus 1, if you've done algebra recently, you might recognize that as something we can factor into n plus 1 squared. And that's algebra applied to step 3. And, you know, I keep checking back on my ignore section what I'm trying to do, and hey, guess what? You know, that's what I had for my sub-goal. I wanted to show that this was equal to n plus 1 squared, and hey, amazingly, I can do that, right? So I've proven this because it follows from that, right? And I know this is true because it follows from that, and this is true because it follows from that, and this is the hypothesis that I'm assuming is true. So given P of n, I have shown that this is a true statement. And the reason I wanted to do this is because this is what P of n plus 1 says. So now I can say P of n plus 1 is true. And that's the definition of P of n in step 4. And therefore, P of n does imply P of n plus 1. Right? Because by assuming P of n, we can show P of n plus 1. And so we have proven the inductive step, and we proved the base case, and mathematical induction tells us, therefore, P of n is true for all n bigger than or equal to 1, and the reason is mathematical induction. And that's what we're trying to show. And so that's a proof using mathematical induction that the sum of the first n odd numbers is always equal to n squared.
2n plus 1 is the next odd number.
Correct.
Okay. That makes more sense. I just thought you just yanked your article there.
Okay. All right, let's do one more mathy one, and then we'll switch to some different flavors of this. But let's prove a proposition about adding powers of 2. So let P of n be the proposition 1 plus 2 plus 2 squared plus 2 cubed plus dot 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 plus 2 to the n is equal to, and anybody know what this is equal to? This is a Pop 250 quiz. Here's a hint, write this out in binary.
I don't know. What is it?
So binary is weighted positional notation, so if you add the first 4 powers of 2 and you write it in binary, it looks like this. And so if you have n bits that you're using to represent integers, the largest integer you can write with n bits is 2 to the n minus 1. So 16 bits, you can go up to 65,535. That's 2 to the 16th minus 1. 32 bits, you can go up to about 4 billion. That's 2 to the 32nd minus 1. And so since this is just, an n-bit number comprised of all ones, this turns out to be 2 to the n plus 1 minus 1. And that's a useful digital logic thing to know. And so we can state this as a proposition, but I don't think we've ever proven this in any of our classes, like in 250 or something like that. But if you work with enough binary, you kind of internalize this fact. When you see an 8-bit number containing ones, you immediately think 255, because that's 2 to the 8th minus 1. But it turns out we can prove this pretty easily using mathematical induction. So let's prove P of n for all n bigger than or equal to 1. Alright, so step 1, this is our base case. P of 1 says, if we add up the powers of 2 up to and including 2 to the first, so 2 to the 0 plus 2 to the 1, this should be equal 2 to the 1 plus 1 minus 1. Well, this side is 3. This is 2 squared minus 1. That's also 3. This is true. So base case, usually not too bad. Second step is the inductive step, which says prove P of n implies P of n plus 1, where n is some number bigger than or equal to 1. And again, this is a single proposition. We're not trying to prove this is true for all n. We're just trying to prove that, if you pick any n, this will imply that. Alright, so how do we prove P of n implies P of n plus 1? So same start as usual. Step 1, P of n, that's our hypothesis. Step 2, let's write out what P of n says. 1 plus 2 plus 2 squared plus dot 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 plus 2 to the n equals 2 to the n plus 1 minus 1. That's the definition of P of n. And now I'm going to, mark off a section, ignore, and I'm going to think out loud. I want to prove P of n plus 1. That's my goal. And P of n plus 1 says 1 plus 2 plus dot 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 plus 2 to the n plus 2 to the n plus 1 equals 2 to the n plus 2 minus 1. Right, that's what P of n plus 1 says. If I can prove this from here, I'm done. I can state P of n plus 1 is true, therefore P of n implies P of n. That's the inductive step, mathematical induction, etc. So I've got a sub goal, which is to try to show that this thing is true. And what I've got so far is this thing, which again looks pretty close to this in some ways. The right side, well, that's pretty different. I have to multiply this by another 2. But the left side of this and the left side of this look pretty close. And it looks like if I were to add 2 to the n plus 1 over here, this left side would look exactly like that left side. Right? So we're going to try that. So I'm going to add 2 to the n plus 1 over here, and this is going to be equal 2 to the n plus 1 minus 1 plus 2 to the n plus 1. And the reason for this is I'm adding 2 to the n plus 1 to both sides of statement 2. Well, this left side of this proposition 3 now is exactly the left side of this proposition, but the right side is not the thing that I'm looking for. So now my goal is, can I change this right side to look like this? And if I believe this proposition is true, I've got to believe that there is some way to change this into that. So does anybody see anything I can do to change the form of this and maybe get it into this form?
We could do log base 2, maybe.
Effectively,
You could do something like, I don't know.
go for it if you can.
No, I was thinking multiplication, but it's addition.
There might be a way to use multiplication here, and it's related to log base 2 in some way. Let me throw in some parentheses here. How can I simplify this expression? 2 to the n plus 1 minus 1 plus 2 to the n plus 1.
2 times 2 to the n plus 1.
Why not, Pull that out, put a 2 in front. Well, this sum of the first, n plus 1 powers of 2 is equal to 2 times 2 to the n plus 1 minus 1. And can I simplify that further?
Yes, you can add a 1 to the power of the 2.
There we go.
N plus 1.
This is 2 multiplied by itself n plus 1 times, and if I multiply by another 2, that's just 2 multiplied by itself n plus 2 times. It's a law of exponents. And now something glorious has just happened. I've just proven that this is equal to that, and in my thinking out loud section, I observe that this is what P of n plus 1 says. So I've just proven P of n plus 1. So go ahead and state that, P of n plus 1. And the reason is that's the definition of our propositions when we look at proposition 4. Therefore, P of n implies P of n plus 1. And now if we take that inductive step and we put it together with the base case and we use mathematical induction, P of n is true for all n bigger than or equal to 1. The reason is mathematical induction. And that's what we were trying to show. Alright, so recapping, there's a bunch of things going on here. First is the idea that we're working with families of propositions, and we're trying to prove that an entire infinite family of statements is true. And we're using this technique called mathematical induction, which I have claimed says that all we have to do to prove that this infinite family of things is true is prove two things. Prove that it's true for some base case, and then prove this inductive step. Prove that if something is true for n, it's also true for n plus 1. And the power of mathematical induction is this idea that if we prove those two things, we are guaranteed that we've proven an infinite number of things. Right? So if we prove that a proposition is true for 1, and we prove that if it's true for n, it's true for n plus 1, we can say it's true for all n. Right? This theorem is called mathematical induction. Just looking at this does not necessarily follow from these two things. But if you do a very, very careful proof, and you make a few really interesting assumptions, what we call axioms, you can prove that this follows from those two things. And we're not required to prove that this follows from those. We can take that as a given. Just like, we can take as a given that a plus b equals b plus a. That's the commutative property of addition. Well, we can take as given mathematical induction, which says if p is true for 1 and if pn implies pn plus 1, then p is true for all n bigger than or equal to 1. So that's the guts of the machinery of it. And then to use this to prove things about families of propositions, we usually start off with, first we prove a base case, and that's usually a demonstration, one proposition that we're trying to prove is true. And proving p of 100 would be easy. Just add up the first 100 powers of 2 and show that it's 2 to the 101st minus 1. It would take a while on a calculator, but it's straightforward. It's not easy. It's straightforward. So proving any particular p of n is straightforward. Proving it for all n, we got to do these two steps. First prove it for say 1, and then prove that if it's true for n, it's true for n plus 1. And so we go into a sub-proof, right, a separate part of the problem, and we say, let's suppose p of n, let's write out what that means, do some magic, and there's always this magic step in the middle, sprinkle the right kind of pixie dust on it, and all of a sudden, we find that p of n plus 1 is true. And now we've got all the pieces, we put it in a nice little box, wrap it up, put a bow on top, that's saying, p of n implies p of n plus 1, and therefore p of n for all n by mathematical induction, QED. So most of the work, when you're scratching your head over these questions, is coming up with this step in the middle. But there's all this legwork to do in the beginning, and then all this wrap-up to do at the end, and those are really, really important. And a lot of times when we're doing inductive proofs, since this is the part that is different from problem to problem, and it's the part that takes the most effort, sometimes our whole proof ends up just being this one piece, and it's not a complete proof, and you can't really get full points on an induction problem if you just have this piece of the proof. And this is a nice warm-up. Stating the family of propositions, stating what you're trying to prove, picking a base case, showing that it's true, stating what you're trying to prove inductively, starting the inductive proof, that's very kind of mechanical, algorithmic. It's going to be kind of the same thing every time. That's a nice way to ease into the really tricky part of the proof. And while you're doing that, you're getting more familiar with what this proposition says and so on and so forth. And then you go to the whiteboard or the paper and you try some things, and and stare at this and scratch your head and listen to music and walk around, and eventually you see a way to show P of n plus 1, and then you like try to clarify that process, write it out, you know, in a nice neat presentation, and then don't forget to like wrap it up in a bow at the end, right? Don't just come here and say I'm done, right? You've done the hard work. Go ahead and present it to the reader in complete form. Hey, this means P of n plus 1 is true. That means P of n implies P of n plus 1, which was the inductive step I was trying to show, and so now I can say P of n for all n, that's mathematical induction, and now I'm done with my proof. So next week's homework, you'll get a bunch of questions to work on, and there's a bunch of questions in the text. This is the end of chapter 3. I think it's section 8 in the text on mathematical induction. So other questions up to here? So let's do a less mathy example. And this not only is going to spare us from thinking about a lot of deep math, but this is going to be a lead-in to some of the stuff that we're starting to do in 222, CSE215, with recursive algorithms for trees. And so this is a really, really key example here. And it's going to be kind of weird to begin with. But when we're done with this, we're going to come back and look at what we've done from the perspective of a computer programmer. And we're going to see something that may be kind of surprising and hopefully pretty delightful. So our goal here is to tile a kitchen floor, right? So we have a kitchen. And you know it's square, right? And we want to get, you know, little floor tiles and use that to cover up the floor. And it turns out, you know, there's one section of the floor that has a pipe coming out. And it might be, you know, off in a corner or something like that, but we know there's one spot in this floor that we don't want to tile, because it's got something coming out of it. But the rest of the floor we want to cover with little square tiles. And we want to do this in a way so, you know, the tiles go from edge to edge, they don't overlap, and so on and so forth. And we go to Home Depot or Lowe's and we price out tile, and it's really expensive, you know. And we can't afford to buy the tiles we need to cover the floor, and so we get really sad and we walk out of the store. We're walking back to our car, and there's this guy in the parking lot, and he's like, "Psst, hey, come over here. I hear you're looking for tiles." And I'm like, "Yeah." He's like, "I'll get you a good deal. I'll get you tiles for, you know, 1/10 the price of what Home Depot's charging." And I'm like, "Okay, cool." And he's like, "Yeah, there's just one complication. The tiles aren't square." And you're like, "What?" And he says, "Yeah, they got this funny shape to them. So the tiles look like this. They're little L-shaped pieces. And it's like 3 little tiles, but they're all stuck together in the shape of an L. And you know, that's kind of weird, and you're not sure where this person got this box of L-shaped tiles, but they're 1/10 the cost of tiles from the store, right? And that's within your budget. So you say, okay, I'll take a box of these L-shaped tiles. And you get home and you've got a whole bunch of these. And you've got enough to cover the whole floor. The question is, can you cover your floor with these L-shaped tiles? Now, you don't have the equipment to cut them. You don't want them to overlap. And you want to cover every piece of the floor except this one square that's missing. And the question is, can you do that? And it depends, right? Now, if my floor, you know, was something like this, and I wanted to cover all 4 squares, I can't do that with this little L-shaped piece of tile. I could cover 3 squares, but I have a piece missing. And if my floor looked like this, I can absolutely tile that. Because I could put one tile, you know, right here, and I could use the other one right here. But if my floor is like 2 by 4, there's no way I can tile that. I'm going to have 2 squares left over. Alright, so you buy these boxes of tiles and you're really excited and you get home and now you're like, can I actually do this? You're not worried about how to do it yet. You just want to know, can I do it? Now, fortunately, your floor is square. And if we think of these tiles as being, you know, 1 inch on each side, so this is 1 inch, this is 1 inch, 1 inch, 1 inch, 1 inch. So this is, you know, 2 inches high and 1 inch across. And so the dimensions of your room are n by n. Well, let me call it, you know, k by k. I'm going to save n. All right. So here's the thing. It turns out if k is a power of 2, you can use these tiles to cover your floor. That's a theorem. So if your room is 16 by 16, you can tile the floor. We already saw if it was 2 by 2, you could tile it. If your floor is 1024 by 1024, you can tile it. If it's 2 by 4, it turns out you can't. But if it's a square room and each side has a length that is a power of 2, you can cover the floor with these L-shaped tile pieces, as long as you have one spot that you don't want to cover. And so we can call this the fundamental theorem of floor tiling, because I don't think there is such a thing yet. All right, so let's prove this, and we're going to prove it using mathematical induction. So I'm going to state the fundamental theorem of floor tiling as a family of propositions. So let P of n be the proposition. You can tile a 2 to the n by 2 to the n floor with one missing square using L-shaped pieces. So other than the 2 to the n part, there's really nothing mathematical going on here. This is a physical problem of placing these tiles in the right places and the right orientations to cover the floor. So P of n is the proposition that if your room is 2 to the n by 2 to the n, you can tile it with these L-shaped pieces. And our goal is to prove P of n for all n bigger than or equal to 1. And we can prove this using mathematical induction. Okay, so how are we going to do this? First, we're going to prove a base case. So step 1, prove P of 1. Okay, what does P of 1 say? It says, P of 1 says you can tile a 2 to the first by 2 to the first room. In other words, a 2 by 2 room with one missing square, you can tile it with these L-shaped pieces. Well, if I draw a 2 by 2 room with one missing tile, it looks exactly like one of these 4 situations. Those are the only ways I can have a 2 by 2 room with one missing square. Right? Because there's only 4 squares in the room, so my missing square is either there, 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 or there. And in this case, I can just take one of my tiles and pop it down right here. And in this case, I can take my one tile and pop it down here. And in this case, I can rotate it into that position, and in this case I can rotate it into this position. And in any of those 4 possible cases, I'm done. I've tiled my floor. I used one L-shaped tile, I didn't cut it, and I covered every piece of my floor except for the one square that was missing. So we can demonstrate that this is true. Now, I don't know how you write that as a formal mathematical proof. You could, but it would be cumbersome. But we're just kind of waving our hands now because, you know, we're in the parking lot of Home Depot. So we can prove that P of 1 is true by just seeing, you know, what it says. And in each of these cases, yeah, I can tile the floor. So clearly something's going to happen in the inductive step. So step 2, prove P of n implies P of n plus 1, where n is some number bigger than or equal to 1. So prove that if you can cover a 2 to the n by 2 to the n floor, you can cover a 2 to the n plus 1 by 2 to the n plus 1 floor. If we can prove this, we're done. We can prove P of n for all n by mathematical induction. Everybody with me so far?
Yeah.
All right. So how do we prove this? Let's suppose, so what is P of n plus 1? It says, you know, something about a 2 to the n plus 1 by 2 to the n plus 1 room. So let me draw a picture of a room where each side is 2 to the n plus 1 by 2 to the n plus 1 squares, inches, whatever. And I'm going to do something interesting. I'm going to break this into 4 sections. And each of these sections is going to be a little subsection whose length and height are 2 to the n. So this is 2 to the n, 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 and so on. Right? 2 to the n plus 1, if I cut it in half, I get 2 to the n. So I have 4 smaller rooms. And remember, there's one square missing somewhere. So let me just suppose that, you know, I'm missing a square right here. Alright, so step 1, P of n, that's a hypothesis. I'm not going to be able to write most of this as a formal proof, but I want to put that down so we remember that P of n is true. Well, let's just look at this upper right corner right here. What's the situation here? This is a 2 to the n by 2 to the n room with one missing square. Can I tile this upper right subroom with my L-shaped tiles?
I would assume yes.
Absolutely. Why? Because P of n is true. Right? We're assuming P of n is true, and this is a 2 to the n by 2 to the n room with one missing square. Well, P of n says I can tile a 2 to the n by 2 to the n with a missing square. So I can cover... Say again?
Can you fill the other rooms, though?
Well, I can cover this upper right quadrant completely. So I've got a quarter of my problem done. But does P to the n tell me that I can tile this section?
I don't know.
It probably says I cannot. It says that if I was missing a tile in this quadrant, I could cover that. But I'm not missing a tile. I'm only missing one tile in my whole room, and I just happen to say it was here. So P of n does not tell me that I can tile this region. Unless I remove a square. So I'm just going to remove one square down here in the lower right corner. Suddenly I'm set up. Right? This is a 2 to the n by 2 to the n room with one missing square. P of n says, hey, you can tile all of that, except for that little corner that I took out. Well, now I got half of my room tiled, except I'm missing one corner. Well, how about this lower left corner? Same thing. I'm just going to ignore one little corner up here. P of n tells me I can cover all of this with L-shaped tiles. Got one more quadrant to work with. I'm going to take out a corner from that. This is a 2 to the n by 2 to the n room with one missing tile. P of n says, hey, I can cover this. I'm almost done, except I'm missing 3 tiles, which happen to be in this L-shaped pattern. So I'm going to take one more tile, and I'm going to cover this. And bingo, I'm done. I've tiled my entire floor, minus that one missing piece, using L-shaped pieces. And so I've proven P of n plus 1. And so P of n implies P of n plus 1. And therefore P of n for all n by mathematical induction. And we're done. Now, the intuitive step here of taking out this corner and this corner and this corner, that's magic pixie dust above my pay grade, right? Somebody really clever came up with this idea to do this proof. And I'm not worried about how would we come up with that inspiration. We're taking this as a proof that we're looking at, and if we follow each step, when we keep nodding our heads, when we get to the end, we've got to conclude, hey, you know, P of n is true for all n bigger than or equal to 1, and the fundamental theorem of floor tiling must be true. And so it's a demonstration of applying the steps of mathematical induction, even if it doesn't leave us with a notion of how we would come up with this on our own. That's not the goal. The goal is to see if we believe that this result is true. So questions about that. Does anybody not believe it? Or does anybody want to go back over some of the steps for this in order to believe that this is a true result?
Are we sure that you could actually fit the tiles in the right pattern for that weird corner thing?
This is a 3 tile section, right? 1 inch there, 1 inch there, 1 inch there, and I've
saying for the rest of the room, are we sure that the tiles would actually fit in a way that the very corner piece of the room could be?
We have to believe that because we believe P of n. And P of n says if I take out any square from a 2 to the n by 2 to the n, I can tile the rest of the room. And so if I take out that square, right, I must still be able to tile the rest of the room. And it's not saying, you know, there is a tile you can remove that makes this possible. It's saying if you take out any one square, you can tile the remaining floor with these L-shaped pieces. Now, we don't know how to do this tiling, but if we believe P of n, which was our hypothesis, we have to accept the fact that there is a way to tile this upper left region with one spot missing right there. But what if we wanted to actually tile a floor? What if this wasn't just a theoretical exercise, but I actually had a box full of tiles and a floor with a missing spot in it, and I wanted to put down these tiles? This doesn't really tell us how to do that, right? It just tells us that there is a way to do it. But in fact, it actually does tell us how to do it. So we can get an algorithm out of this proof. So imagine the following situation. You do this and you're delighted with this and you say, hey, you know, I've got a new business idea. So you buy an infinite supply of these L-shaped tiles and you put a sign in your window that says, you know, floor tiling by Nick, you know. I'll tile your floor with one missing tile. And so, you know, people come to me and they say, hey, you know, here's my kitchen floor. It's, you know, 64 by 64 with a missing tile, and I'll go in there and I'll put down the tiles and, you know, they're happy and they'll give me money, right? So that's my new business model. Well, you know, I've done this, so I know it's possible to tile, but I don't actually know how to do that tiling. So, you know, I got my first customer, and they've got a 64 by 64 floor. And I'm super excited. And I've got my box of tiles and my glue, and they're gone for the day, and here's my 64 by 64. I'll just, you know, keep this missing piece up here. And I'm going to tile the floor. And I have no idea how to do this. You know, I start putting the tiles down, and I bring them out over here, and I get to the end, and I don't have enough space there, and so I back up. And, you know, there's a bunch of ways you can put down that many tiles. How am I going to do this? And so I try, you know, a few times, and can't figure it out, so I go have a snack, you know, and get some coffee and so on. And while I'm walking around, I stumble across a building, and it has a sign in the window, and it says, you know, 32 by 32 floor tiling, cheap. And I think, hey, okay. So I go back to the house, and I put down some blue painter's tape, and I mark this off into a series of 32 by 32 squares. And first I take, you know, this 32 by 32 section with a missing tile, and I go to this other store and I say, hey, can you tile this floor for me? And they say, sure. And they come over and they pop the tiles down here. And then I say, hey, you know, here's a 32 by 32 room. Can you tile it except for that corner? And they say, sure, and they pop some tiles down. And then I say, here's another 32 by 32 with a missing square, and they tile that. And I say, I got one more job for you. Can you tile this room with the missing? And they do that. And I pay them. And I say thanks. And now I take one L-shaped tile and I pop it down here. And I'm done. And the owners come home and they're delighted, and they give me hopefully more money than I spent getting those other sections tiled, right? So I can do this as long as I know, you know, there's a business across town that'll tile 32 by 32 floors. So now put yourself in the mindset of the person who owns that store. They tile 32 by 32 floors all day long. They go to a place and it's 32 by 32, and there's, you know, a missing spot somewhere. And that's their deal. They'll put down L-shaped tiles to cover this. Well, how do they do their job? Because I don't know how to do a 32 by 32, so they split this into 4 squares. And each of these is a 16 by 16. And they find another business that tiles 16 by 16 floors. And they say, hey, can you tile this area, you know, with that missing square? And they say, sure. And then they say, can you tile this area and this area and this area? And they get these 4 quadrants tiled except for those missing spots. And then they drop down a little L-shaped tile right here, and they're done. And they come back to me and say, okay, I tiled your 32 by 32. So they can do their job as long as they have a friend who can tile 16 by 16 pieces. And how does the person who does 16 by 16 rooms work? Well, they need to know someone who can do 8 by 8 pieces. And they do the same thing. And how does the person whose job is to tile 8 by 8 floors get their job done? They need someone who can tile a 4 by 4 room. And how does the business that tiles 4 by 4 rooms work? They just need to know someone who can tile a 2 by 2 room. And so they go to the very busy business that tiles 2 by 2 floors with one missing spot. And they pull out their chart and they say, okay, well, if the missing spot is right here, I'll just drop a tile right here. And if the missing spot is there, I'll drop a tile there. And so they can do their business, which is to tile a 2 by 2 floor with a missing spot. And they deliver those solutions to the people who are doing the 4 by 4. And they deliver their solutions to the people doing 8 by 8 and so on. And the person who's tiling these floors, they are super, super duper busy. But at the same time, their job is trivial. They can tile these floors because they have a map that tells them exactly where to put down those tiles. On the other hand, my job, which is to tile the 64 by 64 floor, is really simple as long as I have someone who can tile the 32 by 32. So one way of thinking about this, how do I run my business that tiles 64 by 64 floors? I have to subcontract to lots of different people. Well, I subcontract to one business that can do 32 by 32s. And I get them to do this quadrant, this quadrant, this quadrant, this quadrant, and then I only have to actually place one piece. And it'll be a piece, you know, either shaped like that or rotated one of 4 possible ways. So as long as I can find, you know, a subcontractor to do the 32 by 32, I can do the 64 by 64. And the subcontractor who does the 32 by 32, their job is very easy as long as they can find someone to do a 16 by 16. All right. Here's the trick that makes this actually work. I'm the person who's doing the business that tiles 64 by 64 floors. The subcontractor I hire to do the 32 by 32s, that's also me. I just put on a different cap. And my cap says, you know, super duper 32 by 32 floor tiler. And while I've got that cap on, I'm just tiling 32 by 32 floors. And to do that, I'm going to tile a 16 by 16. Who do I find to do that? I do that myself too. I take off my 32 cap, I put on my 16, and I say, hey, I tile 16 by 16 floors. And I keep doing this until I need somebody to tile a 2 by 2 floor. And at that point, you know, I just pull out this handy little chart, and I say, oh, there's an empty spot there. Okay, I'll just put a tile down there. And I hand that solution to the version of myself that was trying to do a 4 by 4 floor. And they put that together and eventually come up with the 4 by 4, and then you take 4 of those and you get the 8 by 8 and so on. And I don't need a separate contractor to do that. I can do that myself. And so this weird problem of tiling floors, right, with these L-shaped pieces, we can do this inductive proof that it's always possible, but buried inside that proof is actually an algorithm for how to do this floor tiling. And the algorithm has this peculiar structure where we can solve this 64 by 64 problem by first solving some smaller problems, some 32 by 32 problems. And this is exactly what we're starting to do in CSE215 with binary search trees. If we have a tree set up like this, and we want to print it, it's really easy to do. All we have to do is print the stuff that's on the left of the root, and then print the root, and then print the stuff that's on the right of the root. And this is like, you know, going to a subcontractor and saying, hey, I got a little tree for you, can you print this? And they print it out, and they tell me what the nodes are, and then I print out the root, and then I take this, and I say, hey, can you print this tree? And they print that out for me, and I put those all together, and bingo, I've printed out the whole tree. And the only thing I ever really had to print was the root. And I let, you know, this subcontractor print out these two. But of course, when we code this in C, we don't have a separate function. We don't have a big tree print that calls a small tree print. We call the same print function. And so these kinds of mathematical proofs are very, very closely tied in to these recursive algorithms that we're going to be doing for the rest of CSE 222 and 223 in spring. And so that's probably a fairly nebulous connection, but I want to start making these links between these concepts. And as we're doing recursive algorithms in 222, you can be kind of thinking about this. And our recursive code always has this sort of base case, you know, if the root's null, just return. That's this thing up here. Otherwise, you know, get the answer for n plus 1 by using the answer for n. That's this inductive step. And as we go through mathematical induction, you can kind of be thinking about, you know, these recursive algorithms and seeing if there's a way to think of linking this back into the recursion we're doing in dealing with trees and other data structures. All right, so that's my first introduction to mathematical induction. I don't expect it to be crystal clear. If it feels kind of murky and confusing and maybe suspicious, you're exactly where you should be, okay? Because this stuff is kind of murky and suspicious and unclear at first. But we're going to keep working on this throughout next week and possibly the following week. And we'll have homework questions that get posted next week to give you practice on this. But we're going to keep alternating between, doing some of these more mathematical proofs where we're dealing with, equations, and some of these more kind of non-mathy proofs where we're dealing with, physical processes, things like that. And we'll develop both of these more and more and try to get a better idea of how this proof works out and also how it relates to algorithms. So we'll definitely keep going with this for a few more classes. All right, that's all I got. I'm out of time. Have a great afternoon, and I will see people next time.
Thank you. Have a good day.
Thanks, you too.